Okay, so let's look at the first question of the tutorial. And here we're given the vapor pressure of dichloromethane at 24.1 degrees Celsius is 53.3 kilopascals, and its enthalpy of vaporization is 28.7 kilojoules per mole. And then we're asked to estimate the temperature at which its vapor pressure is 70 kilopascals. Right, so immediately we know it's a liquid vapor equilibrium, or transition. So in other words, we need to use the Clausius-Clapeyron equation in the form of ln P2 over P1 equal to minus delta vap H over R, then 1 over T2 minus 1 over T1. Alright, so that's immediately our first thing that we know, because we're dealing with liquid vapor transitions. We're given enough information. We're given a vapor pressure at a temperature, we're given another vapor pressure, and we're asked to calculate its corresponding temperature. We're given the enthalpy, we have R. So it's just a straightforward application of this equation and just the calculation. Okay, so basically we just have to plug in the values, so we can go through that. So looking at this, we just have to ensure that essentially we keep the values units the same. So we're given both pressure values in kilopascals, so we can keep that the same because we're dividing them with each other. So if we go that route, so we keep them the same. So in other words, let's make P2 so in other words, if we were going to calculate T2, so then P2 has to be 70 kilopascals. So 70 kilopascal divided by 53.3 kilopascal is equal to minus, so then 28.7. This just has to be joule per mole, so then of course we multiply by 10 to the power 3 joule per mole divided by 8.3145 joule per Kelvin per mole. And then this, we are left with, we want to calculate T2, so we leave that. And then T1 is 24.1 degrees Celsius. In other words, it's 24.1 plus 273.15, which is 297.25 Kelvin. Okay. And then we can calculate these values on their own. So this is 0.27256 and so on. This is minus 3451.8 and so on. There's only a Kelvin that remains here because the joules cancel, the per moles cancel, and the Kelvin goes on top, right? And then on here we're left with 1 over T2 minus 1 over 297.25 Kelvin. Okay. Then we're going to divide these two values with one another. So we're basically left with 1 over T2 minus 1 over 297.25 Kelvin equals to minus 3451.8 divided by 0.27256 and so on. In other words, 1 over T2 is equal to minus 3451.8 over 0.27256 plus 1 over 297.25 Kelvin. And this is both. So this is Kelvin, of course. Kelvin, and this is just a unitless quantity. So, and this is per Kelvin. So you'll see it actually, oh no, goodness sake, this is, I made a little error here. This used to actually switch around. Oops. The 0.27256 is on top, and the minus 3451.8 is below. It's always useful to carry the units because then you can immediately see if you're doing something wrong. So 2.7256 is below, and the minus 3451 is below. So then we have per Kelvin per Kelvin. So then we say, well, T2 is just equal to 1 over that. So in other words, this whole thing, so I'm not going to rewrite that because that's just a waste of time. You know, I have a life as well, believe it or not. Just the minus that got lost in the movement. That all to the power minus 1. Okay. And that then should equal 304.4 Kelvin. Right. Because, so I mean, it's actually, so it goes to there, and then we go to 304 Kelvin. Because we have given 3 significant figures in everything that we're given at the start. So 304 Kelvin. So 3 significant figures if you want to do it like that. The way that I actually like, so I mean, this way you have to carry around a lot of different numbers. I mean, it's an easier way to calculate it in the sense that you don't have to, so then you can calculate the learner part, you can calculate each thing individually, and you carry it on. The way that I like to do it, I mean, you can of course do it in any way that you like. I like to rewrite the equations for the subject that we want to calculate. In other words, you start with your equation. I just quickly want to write it here for us again. Okay. And then we want T2 as the subject, right? So in other words, first we're going to multiply this thing to the other side. So in other words, we have then R over the vaporization enthalpy ln of P2 over P1, let's put the minus here as well, is equal to 1 over T2 minus 1 over T1. Okay, and then we want T2, so in other words 1 over T1, we bring it here to the left, T1 is going to be minus R over delta vap H ln P2 over P1, and then to get T2, you know, T2 on top, we just have to take the inverse of that, right? So in other words, we invert that whole thing over there. So and then you plug in your values. In other words, we have T2 is equal to 1 over T1. So T1 is then 24.1 plus 273, which is 297.25, minus R, which is 8.3145 joule per Kelvin per mole, over delta evaporation, which was 28.7 times 10 to the power 3 joule per mole. Okay, and that's just times ln of 50. So then we just have to remember which one did we put. So we're calculating T2, and T1 is 24. Then it should be 70 on top. Yeah, 70.0 kilopascal over 53.3 kilopascal. Right, all to the power minus 1. And then you will get exactly the same answer as before. This should give you an answer of 3.285 times 10 to the power negative 3 to the minus 1, and then that will give you 304, round it off again, Kelvin. Right, so, and I think that's the better way to do these problems, is actually to write it in terms of what you want and then just plug in all the values, because there's less chance of you making a calculation error. Yeah. Anyway, but you can, of course, you can really do whatever's easier for you. There really is no right or wrong method. It's all about whatever is best for you. So, if the algebra is easy for you, then you do that. If neither method's good for you, leave the page blank. Yeah, so that's basically it. Just a straightforward application. Of course, if we want to interpret it a bit, I mean, we're at what? We're at a higher temperature, higher pressure, so, in other words, it makes sense. The vapor pressure should be higher at the higher temperature, so because we expect a sort of linear increase with the higher temperature, as the equation dictates. So, yeah, it's not really like difficult, like heavy interpretation we can really, or groundbreaking interpretations we can really give with this kind of work, but it's just the temperature increases with the higher pressure. So the higher pressure, you have to have a higher temperature to boil the liquid as expected. Anyway, right, so that is it for question 1.